Okay, this is calculus, limits part 2. I think last time you looked at limits, we looked at limits with graphs, but today I'd like to show you how we can use limit laws to actually calculate limits. So it's like doing limits via algebra. There are a whole bunch of properties that you need to know. And so let me just take a few minutes to quickly look at those properties, and we'll do an example of each, and then we'll go and mix everything up. So the first property here says the limit as x approaches to a of the value x. So that means when x gives you this number a and you're plugging into this function called x, well, what do you get? Well, what they're saying is replace x with a, so your answer is a. As an example, if I have the limit of x approach to 3 of the function x, well then of course that just equals to 3. Now the next one's a little bit different from before. It says the limit of x approach to a of c. Now c is a constant, like a number, like 1, 2, 3, 4, pi, -5, √5, all those numbers. So as an example over here, if I took the limit as x approach to 3 of the number 1,000, or the function 1,000, see how there's no x? So the 3 doesn't come into play. The answer is just 1,000. Then property number 3 shows you what to do if there's a constant in front of a function. So if there's a constant c in front of the function, and you're taking the limit of that entire function, it's equal to the constant multiplied by the limit of just that function. So an example over here, you see we have a constant 7, and then we have the function x. So I can take out the 7 and write it as 7 limit x approach to 3 of x. And we've done this before. Well, that's the same thing as what we did in property number 1. So that's just 3. So 7 times 3 must give us 21. And addition and subtraction property limits. If you have two functions added, subtracted together, and you want to find the limit of that entire thing, then you're just taking the limit of each individual part. So as an example, here we have the limit of x approach to 3 of 12x minus 5. We're going to break that up into two parts, the limit of x approach to 3 of 12x, and also the limit of x approach to 3 of 5. Now to evaluate that first piece, you see how there's a constant. I'm going to use the previous property, take it out, and now we can just evaluate the limit of x approach to 3. We've done that before. That's just the number 3. The limit of x approach to 3 of a constant of 5 just remains a constant. So 36 minus 5, that's 29. Just like addition and subtraction, there are laws for multiplication, and then of course division. So same idea with multiplication. The limit of two things multiplied together is just the limit of those individual things multiplied together. So in this particular example, I'm going to ask you to break this up. So this is the limit as x approach to 3 of x, and that's the first part. And you're going to multiply that by the limit of x approach to 3 of the function x minus 5. Notice that this function needs to be separated. Subtraction, so just like the previous property, property number 4. And then we can evaluate that just equals to 3. That equals to 3. That equals to 5. 3 minus 5 is -2. 3 times -2, of course, is -6. So that property for multiplication, similar thing for division. So the limit of f of x over g of x is the limit of f of x over the limit of g of x, provided that, now what does this mean? Remember, when we're dividing, what do we have to worry about? And if you said we can't have the denominator equal to 0, you are totally correct. So provided that the limit as x approach to a of the g of x, so your denominator, does not equal 0. Alright, so let's go ahead and try to calculate this limit. I see the limit of x approach to 3 of x plus 4 over x minus 1. And like I said, let's split it up. Now let's go ahead and break down the parts. So in the numerator, you get the limit of x approach to 3 of x, the limit of x approach to 3 of 4, the limit of x approach to 3 of x, minus the limit of x approach to 3 of 1. Evaluating now, this of course equals to 3, 3 plus 4, that's 3 minus 1, that's 7 over 2, that's it. Okay. One more limit property that I want to show you, that's with powers, and then after that I was going to combine all this stuff together and let's see if you can do these questions. So you see how there's a limit of a function raised to the power of n? Well, that just means take the limit of it first and then raise it to the power. So in this particular example, if I were to do this one, I want the limit of x to approach to 3 of x minus 1. We're going to do that first and then raise it to the power. Well, that's hopefully pretty straightforward. Limit of x approach to 3 of x minus the limit of x approach to 3 of 1. And of course that's 3 minus 1, and that's 2 to the power of 4, lovely 16. Okay. By the way, square root, what's that as a power or exponent? Well, it's a power of a half, so if you want to write it as an exponent, you can. If you don't, that's perfectly fine. I'm just going to ask you to do the limit part first, and then take the square root. So I hope you get the hang of this by now. We'll evaluate, that's just 3, that's just 22, that becomes 25, and the answer is 5. Okay? So the next question, and this is actually example number 1 now, so these are all the properties you should know about limits, but think about it, they're just like algebra, so it's nothing really that's too new. What I'd like us to do now is take a look at example number 1, and I want you to evaluate this limit. And as you evaluate this limit, I want you to justify each step, meaning I want you to tell me which property you are using to help you evaluate the limit. Okay? So I think the first thing I'll do is I see addition. So what do you think we should do? Someone give me a suggestion? And if you suggested to split it up using addition, I like that. And so this is using which property? That's property number 4. Okay, so I'll just put a little 4 here. I'll put PPTY, property number 4. Okay, what's next? Well, maybe you want to say, well, that's the same thing as the limit of x approach to 2 of x, and then we're going to raise this to the power of 2, plus the limit of x approach to 2 of 1. So this is the power one, and that's property number 7. I'm just going to put a little 7 with a circle there. I'm just a little bit lazy. Then you might be thinking, well, I want to actually evaluate this limit here. So we plug in 2, so you get 2, and then you square it. Still have a limit of x approach to 2 of 1. Plugging it into a function, I think that's number 1, especially when the function is just x. So there's property number 1. And then I think you have to evaluate this constant part, 2 squared, and the limit of x approach to 2 of the constant 1 is just 1. That's the constant rule, which is number 2. Oops. And now you're ready to evaluate your final answer. 2 squared is 4, 4 plus 1 is 5, then you're done. Okay? And the justification is just those property numbers that I've recorded and circled. Now, in this previous example, you might be thinking, Mr. Lee, that was such a waste of time. I could have just plugged in the number 2. 2 squared is 4, 4 plus 1 is 5, and it works. So you saw that direct, erase that by the way, direct substitution also worked. Now, here's a general property. If the function is a polynomial or a rational function, so that's a fraction, okay, and the value of a that you're plugging in, so you're approaching a, is in the domain, meaning it, for the rational function, it can't make the denominator equal to 0, then always, yes, always, the limit as x approach to a of the function is always equal to the value of the function. So this is like the value of the function, meaning like the y value, the stuff that you're used to, okay? Always. So let's take a look at some of these examples. Number 2 now. You see how this one's a rational function? So I'm thinking, as long as this, when I plug in negative 1, doesn't make the denominator equal to 0, it's great. So let's take a look at what we got. So I'm going to plug this in. Okay, and I'm not going to show you all the steps. I'm just going to plug this in now. So negative 1 minus 2 over negative 1 squared plus 4 times negative 1 minus 3. The numerator becomes negative 3. The denominator becomes 1 minus 4 minus 3. Negative 3, 1 minus 4 is negative 3, negative 3 minus 3 is negative 6. That simplifies to a half. And that's it. Okay. Notice that the value of a, which is negative 1 in this case, is in my domain. right? It's not one of my non-permissible values, so we're good. Okay. Let's try number 3 now. Okay, so I'm going to plug in the limit as x approaches to 3. So I'm going to plug it in as 3 squared minus 9 over 3 minus 3. That's 9 minus 9 over 3 minus 3. Uh-oh, that's 0 over 0. What is going on? Well, let's take a look underneath. It says in number 3, when you substituted x equal to a into the function, so there's my function, my rational function, we got this case, 0 over 0. Now in most cases, this means that the factor, or sorry, x minus a, is a factor of both the numerator and the denominator. Now remember this question here, x approached to 3, x squared minus 9 over x minus 3? We did that last day. Take a look with me again. It's this one originally here, right? X squared minus 9, x minus 3. Don't know if you remember us graphing it out, but the function really became like a line, like this. But the neat thing, or the weird thing, was that at 3 we had that open dot. So this rational function simplified to look like a line, but it had a non-permissible value. So we didn't draw the asymptote, but we drew the open dot. Well, I want you to also understand that okay, before I do this, okay, let's stop here. So because there's a factor of both the numerator and denominator, here's what we have to do. We should factor. Well, what's x squared minus 9 if we factor it? If you see difference of squares, I like it. And notice now when I do this, hey, the factors of x minus 3 cancel out. And so this is really the same thing as the limit as x approach to 3 of x plus 3. Now, provided that x does not equal to 3. You see how our function now, that used to be a fraction, now became just a straight line, x plus 3? Well, that's why the graph looks like a straight line. And if you think of the slope is going to be 1, and you'll see that the y-intercept is 3. So now, with this piece in red, can you now evaluate this limit? I hope so, because if you do now, you get just 3 plus 3, which is just 6. Okay, and confirming what we had last day, the limit as x approaches to 3, see, it gets closer and closer to 6. At 3, it doesn't equal to 6, so the value at 3 does not exist, but the limit at 3, when it gets closer and closer to 3, does exist. And you can see that the value gets closer and closer to 6. Okay? Now, I also want you to understand and not confuse this with something like this, where you have a number, let's say 1 divided by 0. Okay, the top could be any number, by the way, except 0. Any number not equal to 0. When you have this, I hope you remember, this means that the function has a vertical asymptote. Remember those terms, the asymptote? Yeah. Or the limit may or may not exist. Okay? So let's go on to a few more examples, and then hopefully we'll be done very shortly. Okay? Oh yes, one more page. Very good. All right, here's example number 4. The limit of x approach to 0 of 4 plus x all squared minus 16 over x. So once again, I see a rational function. I'm going to plug it in. I know it's not going to work out, but a lot of people don't see that right away. So they just go blindlessly and put things in. So I'll pretend to be one of those people, and I'll blindlessly plug things in. I get 0 over 0. Whoa, 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 whoa. So when you see the 0 over 0, that means there must be a factor involved. Either you take a look at the numerator and try to factor it out, or you can expand and see what happens. Okay? I'll show you both ways. So if you factor, and the other way would be to expand. Okay? If you can see that the numerator can be factored, once again a difference of squares, that'd be 4 plus x plus 4, and then 4 plus x minus 4, then I think that's pretty straightforward and showing that, hey, I now have that extra factor of x right here, right? So you just factor this and you go ahead, cancel, cancel. The limit of x approach to 0, 8 plus x, that gives you 8. Alright, so that was the method using factoring. Of course, if you don't like factoring, you can expand out the numerator instead. So if you were to expand, you get what? 16 plus 8x plus x squared minus 16 over x. And if you were to now continue to just simplify, I believe on the numerator you get 8x plus x squared over 8. Now remember, our goal is to try to eliminate that factor of x somehow. So I hope you can see that the numerator can be factored and you can take out the x. And that's what we wanted. There goes the x. Now we can plug in the limit as x approaches to 0, and then we get our same answer of 8. Ta-da! Alright, example number 5 is next, and I think that cube thing is scaring some of you. So remember how I taught you the extra bits of chapter 4 and how to factor a cubic? Well, this is why you need to know it for calculus. So review your notes from the chapter 4 extra part if you don't remember how to factor a cubic before you attempt this question. So once again, if I were to plug numbers in blindly, I see that we have here 0 on the top, 0 on the bottom. That usually is a key indicator that there is a factor that we need to factor out from the numerator. So, hold on. Okay, so once again, we've got a factor. So if you don't remember, we look at the constant term and you say to yourself, what are the factors of 8? So the possible factors of 8 are really just 1, 2, 4, and 8. But don't forget, it's not just positive 1, it's plus or minus. Okay, so you have actually 8 different numbers that we can choose to make it a factor. The idea is you're going to test points now, and you're going to test these numbers and plug it in to see which one gives you 0. Remember, this is like the remainder theorem. And I'm going to test out 2 because I know 2 actually works. It's 2 cubed minus 8 equals to 0. Yay! Therefore, what I know is x minus 2 is a factor. Now, that should have been pretty apparent to you all because this is the factor I want to get rid of. So now let's take a look at x minus 2, and I'm going to now factor or divide it doing long division. Do you know why I left a whole bunch of space there? Just like how you write numbers, you need to have place value holders, right? Like how you write the number 1008. You don't go 1 and then 8, you go 1008. So same idea. Now let's do some long division. So x times what gives you x cubed? I hope you think it's x squared. Then you go x squared times x minus 2. You distribute and you put it underneath. So once again, if I'm going too fast, please review my notes. Okay, we'll subtract. Get 2x squared. Bring down the 0x. Ask yourself what times x gives you 2x. That's 2x. 2x squared minus 4x. Then we have 4x. Bring that down, minus 8. And this should always be equal to 0 because that means that your remainder is 0. All this work just to factor, so really now what you can do is you can rewrite this limit as the limit as x approaches to 2, and you've got the factor of x minus 2, and you've got this x squared plus 2x plus 4, all divided by x minus 2. This is great because these cancel out, and there you have it. Now you can plug things in. It's a nice polynomial. You know it's going to work. 12. Yay! All right. If you're not tired of algebra yet, guess what? Just a few more. I want to let you know that some forms of the type where you get 0 over 0, instead of having a factor, you're going to use the technique of multiplying by the conjugate, especially when you see these square roots. Now you technically can also do this by factoring, especially number 6, but I'll show you this technique of multiplying by the conjugate as well. So factor method, conjugate method. Okay, let's factor. Oops. Limit x approach to 25. Now, can you factor the top? If you can see that this is equal to 5 minus root x and 5 plus root x, that's great. Because once again, you now are allowed to divide these out. And that's perfect because now I'm left with a nice, easy polynomial. Well, actually, not polynomial, but function, at least a square root function I can deal with. 5 plus root 25. What's root 25? That's 5. That's 10. We're done. Okay. Now, if you can't see that, then you can always try to do this idea by multiplying both the top and the bottom by the conjugate. So we learned this in, I don't know, grade 10, grade 11. We did rationalizing the denominator. Remember, math people, they're very picky. They don't like having roots in the denominator. So in this case, you can multiply both the top and the bottom by the conjugate, which is the same as the bottom, except we change the signs. Doing this now, limit x approach to 25. I'm going to actually not multiply out the numerator. Okay, and you'll see why in a second. But I will ask you to multiply out the denominator. And this is a minus b, a plus b, so hopefully you remember that the middle terms disappear because they cancel each other out. Okay. See how this is now on the bottom? 25 minus x. Whoa, looking good. Bye-bye. And you see you end up with the same thing as before. Plug in the value and you'll get 10. Okay. Now, example number 7 is one I'd like you to try on your own. Okay, I've got this square root, and I'm going to ask you to do this by the conjugate method. Okay, notice if you were to plug in 0 right away, I get 1 plus 0 minus 1 over 0. That's 0 over 0, and that's once again our weird case. So let me get you started off, and then I'm going to ask you to try to finish it off. Find the limit of the square root of 1 plus h minus 1 all over h. And if you're curious what the conjugate is going to be, it's the same part as the root, but with a plus. Okay, you finish this one off, pause the tape, and then come back when you're done. Notice in this case, once again, I did not multiply in the denominator because I know I'm trying to eliminate this factor of h. So I want to keep it visible so I can see the individual h. Because now I know that they can divide out evenly, or nicely, I'll say, and now I should be able to evaluate my limit. By the way, don't be lazy. Keep writing the word limit h approach to 0 until you actually plug in the value. Okay. I know many math professors will take off marks if you don't put the h approach to 0 portion. Okay, there you go. There's the answer 1/2. Okay, your turn. You have this extra time. Go ahead now and work on the questions. Okay. Answers are there too.